Over the last few years, I have covered a number of variations on the Z80 retro computer. And while the original Z80 processor package is now no longer manufactured, production having ceased in 2024, the EZ80 is still in production. This EZ80 chip is a faster and code-compatible derivative that includes built-in RAM and flash memory. This video isn't intended as a tutor on Z80 assembly or machine code, but rather an overview of the architecture of the Z80 processor. The original Z80 chip was manufactured for some 48 years, and when Zilog released it in 1976, it was positioned as a superset of Intel's Z80 chip, adding new instructions, richer register handling, and a more flexible interrupt system, while preserving binary compatibility. Built on an 8-bit data path and a 16-bit address bus, the Z80 can address the full 64 kilobytes of memory that defined early microcomputers. Its internal design combines straightforward elements, a small number of registers with ingenuity, including shadow registers, index registers, and versatile exchange instructions, making this chip exceptionally capable for its time. Today we are going to step through each architectural element, from the elementary 8-bit registers to the sophisticated alternate register set, explaining their purpose, interrelationships, and how the EX and EXX instructions turn the Z80 into a fast, context-switching engine. Firstly, the core 8-bit registers. In a Z80 processor, the registers are like a handful of tiny ultra-fast memory locations that live right inside the chip. Whenever the CPU does something, adds numbers, moves data, or follows a set of instructions, it writes the intermediate results and bits of information into these locations, so it can keep track of what it's doing. Because they are built into the processor, reading from or writing to them happens almost instantly, giving the Z80 a quick way to remember things like the latest calculation result, where it is in the program, or a place in external memory it will need later. The Z80 has several of these registers, each with its own purpose. One holds the main arithmetic result, a few can be paired together to store larger addresses, and another always points to the next step in the program. Together, they give the Z80 a simple, speedy, short-term memory that helps it run programs efficiently. There are several general-purpose 8-bit registers, plus a dedicated flags register. They can be viewed either as isolated 8-bit entities or as components of 16-bit register pairs. At the heart of the processor is the ALU, the Arithmetic Logic Unit, accessed via the accumulator. Think of the ALU in a Z80 processor as the little math and decision-making part inside the chip. Whenever the computer needs to add two numbers, compare values, shift bits left or right, or decide if one thing is bigger than another, it hands the job to the ALU. This part of the processor quickly crunches the numbers or checks simple logical conditions, then hands the result back to the rest of the CPU, so the program can keep moving forward. In short, the ALU is the Z80's built-in calculator and logical judge, handling all the basic arithmetic and decision work that makes a program run. So firstly, we have the accumulator, referred to in assembly language as A, which is used for arithmetic, logic, and data movement. This is the data workhorse, and together with the flags register forms the AF pair. Next, we'll look at the flags register, referred to in assembly language as F. This holds condition flags which are updated by most of the arithmetic and logic instructions. These are not directly addressable by most functions. Firstly, the sign flag. This reflects the most significant bit of the result. Next, the zero flag, set when the result of a calculation is 0. The half carry flag is used for binary coded decimal arithmetic. The parity or overflow flag is for logical operations, overflow for arithmetic. The N flag is the add-subtract flag and indicates whether the last operation was subtraction. The carry flag indicates carry or borrow. These flags are automatically updated by most ALU operations, providing a complex status word for conditional branching. Next, we have a series of 8-bit registers, which can operate in pairs to effectively give you what behaves like a 16-bit register, allowing you to address memory locations in the 64 kilobyte memory space. BC. These are general purpose registers, often used as a 16-bit BC pair. The C register is the default 8-bit I/O port address for in and out commands. D and E. These are also general purpose registers, often used as a 16-bit DE pair. The E register frequently serves as a low byte for memory offsets. HL. Again, general purpose registers, often used as a 16-bit HL pair, often described as the pointer register. The HL addressing mode is the most common way to reference memory. Next, we have the interrupt vector register, which holds the high byte of the interrupt vector table address. This is not part of any 16-bit pair, and is read-writable only via special instructions. Finally, we have the refresh register R. This is incremented after each instruction fetch, and is used for dynamic RAM refresh. The upper 7 bits are readable. The lower bit is always 0. Using register pairs. The Z80 processor treats certain adjacent 8-bit registers as a single 16-bit entity. This design simplifies address arithmetic, stack operations, and data movement. The primary pairs are AF, the accumulator, and flags, often used to push or pop the current status. BC, a 16-bit counter or pointer, also used for input-output port addressing via the C register. DE, frequently a source or destination for block transfers. HL, the primary memory pointer. This is the default indirect addressing mode register. IX, the index register for advanced memory addressing. IY, a second index register, often used for table lookups and stack frames. SP, the stack pointer, points to the top of the software stack. PC, the program counter, holds the address of the next instruction to fetch. The Z80 introduced the IX and IY registers as 16-bit index registers, each split into high and low halves. These registers enable displacement addressing. Internally, the CPU adds the signed 8-bit displacement to the 16-bit index value, then performs the memory read or write. This feature is invaluable for data structures like arrays or records, and for building compact code that would otherwise require multiple load instructions. The stack pointer and program counter. The stack pointer is a dedicated 16-bit register that the Z80 uses for call, return, push, and pop operations. The stack grows downwards, decrementing the SP register. The program counter is the internal instruction pointer, automatically incremented after each fetch, unless altered by a jump, call, return, or interrupt. Both of these registers are not directly readable or writable by ordinary instructions, but they can be manipulated indirectly through a number of load or exchange instructions. The alternate or shadow register set. One of the Z80's most distinctive features is a complete shadow copy of the core register pairs AF, BC, DE, and HL. These alternate registers are usually denoted with a prime suffix. They are exact replicas of the primary registers, each with its own dedicated physical storage within the CPU. The alternate set does not include the index registers IX and IY, or the special registers, the interrupt and the refresh registers. So why create a second set of registers mirroring the ones we have already covered? We are so used to computers doing multitasking and juggling many activities at once that we tend to forget how simpler processors with only the one processing core handled dropping one task and started another. This was done using a technique referred to as an interrupt, allowing the processor to be signalled that it needed to stop what it was doing and handle something else. The dilemma for programmers was how to park what the processor was working on while switching context to the new activity. Without the shadow register set, this had to be done by pushing all the registers onto the stack and retrieving them later. With rapid context switching, when an interrupt occurs, the CPU can instantly swap the main register set with the shadow set using a single instruction, thus preserving the interrupted task's state without having to push all the registers onto the stack. Multitasking. Software that implements cooperative multitasking can switch between two execution contexts, for example, a foreground task and a background routine, by swapping these register sets, saving and restoring only the stack pointer and program counter. Nested subroutines. Some compilers generate code that uses the shadow set for leaf subroutines to avoid the overhead of saving registers onto the stack. However, you don't need to swap all the registers at once. The EXX command exchanges the BC, DE, and HL register pairs with their shadow counterparts. The AF register is not touched by the EXX command. There is also an EX command that swaps only the AF register with its shadow version. Exchanging register contents with memory locations. Going beyond just swapping between primary and shadow registers, the Z80 instruction set offers memory register exchange instructions. For example, swapping the 16-bit value at the address pointed to by the stack pointer with the contents of the HL register pair. These are powerful for saving or restoring a register pair on the stack without separate push and pop instructions. When the Z80 processor was launched in 1972, it was lauded for having 170 instructions. By 1976, the Z80 had raised this bar to 158 basic instruction types, expanding to 700 to 1,000 unique opcode permutations. Altogether, these features give the Z80 a flexible yet low overhead register architecture that has kept it relevant for hobbyist projects, embedded systems, and retro computing enthusiasts for nearly 5 decades. Hopefully, you will have enjoyed this short delve into the innards of the Z80 processor. But that's it for today. Thank you for watching.
Thank you for watching today's video. Please feel free to click on the link in the description below to discover more videos.